Hi there, welcome back. Having learned the basics of circuits, we're now ready to tackle an example that deals with a more complex circuit. So in this example, we'll take a circuit with 4 resistances, and our objective is to determine for each resistance the current through the resistance, the potential difference across it, and the power it dissipates. We'll do this by following solution steps that work with more complex circuits. First, we'll take pairs of resistors and determine if they are in series or parallel. That is not always obvious in more complex circuits, so we got to pick the pair that's the easiest to determine the arrangement. And then using this technique, we will reduce the circuit to a simpler analogy or analog of it, one step at a time. So let's get on with it so you can see how all this is done. So here's the circuit we've been given to analyze. There is a 15-volt EMF battery that's powering a circuit with 4 bulbs. We got bulb A of 5 ohms, bulb B of 15 ohms, bulb C of 10 ohms over here, and bulb D at the bottom here of 20 ohms. And our task is to figure out the current through each bulb and the potential difference across each bulb. So as you look at this, it's really hard to say if bulb A is in series with bulb B or not. And in fact, we know that it's not because the current going through bulb A is not all going through bulb B. It's splitting over here. And we also know that it's not in parallel because we can't conclusively say that the potential difference across bulb A and that across bulb B are equal. In fact, that's not true either. So these are not in series or parallel. Same thing with B and D. We can't say that the same current goes through them because there's junctions over here, and we can't say that the potential difference across B is the same as that across D because C is in between. So that's what makes this circuit complex to analyze. Well, when we have a complex situation like this, we got to simplify it one step at a time. And in the very first step, what I'm going to do is take a look at this and realize that resistances C and D, those 2 bulbs, are in fact in series. Even though I have shown this as part of a triangle and turned this wire over here, there is no other wire going off of this corner here. So all of the electrons or all of the current going through bulb C has to be going through bulb D as well. So C and D are in fact in series. But even before I analyze that, I'm just going to simplify this in terms of drawing. The other thing that makes this circuit complex is how it's been presented to us as a triangle over here. So I have redrawn the circuit. I have not done anything but simply redraw it into an arrangement that looks more familiar to us. I got this 15-volt battery. There is bulb A, just like it was before. And instead of that triangle, I've simplified it to show one loop was going from A to B back to the battery. So I got A to B back to the battery. It's the same thing. I've just changed the shape of it. Rather than it being slanted, I've made it go straight down. And then we see that C and D put together share the same junctions as B. So here I've got C and D, and when they're put together, they share the same junction or same potential difference that is across B. So just by redrawing it like this, I've got a circuit that is identical to the one that was given to us, but easier to analyze. Our next step is to take a pair of resistances and figure out if they are in series or parallel. As I said before, A and B, we cannot make a conclusive decision. It's neither in series nor in parallel. Same thing with B and C and B and D. They're not in series or parallel. But C and D are in fact a series arrangement. So my first step in simplifying this circuit is to combine C and D. We know that the equivalent resistance when you have resistors in series is to simply add them up. So in this case, the equivalent resistance, let's call it equivalent resistance CD, equals the resistance of C plus the resistance of D. And so if I use the values, C was 10 ohms, D was 20 ohms, so that'll give me 30 ohms. So I'm going to draw that simplified circuit over here. So there's a lot of redrawing the circuit in this process where we are simplifying it one step at a time. So I've got A, I've still got B, nothing has changed for those. And now I've simplified it to a CD resistance over here of 30 ohms. And B is still the same as it was, so I'm not going to write the value of 15. and A is 5 volts as it was before. So now I've got a circuit that's equivalent to the circuit I started with, but instead of 4 resistances, I only had 3 resistances, so it's getting simpler. All right, so now let's reanalyze this and see which 2 pairs of resistances we can conclusively say are in series or in parallel. Once again, A and B are not in series because of the junction, and they're not in parallel because they don't have the same potential drop across them. But now we can see that B and CD, this new combined resistance, are in parallel. So my next step will be to combine B and CD, realizing that they are in a parallel arrangement. So in order to combine resistances in parallel, we know that 1 over R equivalent equals 1 over RB plus 1 over RCD. And so this will be 1 over B was 15 ohms, CD was 30 ohms, and this simplifies to 2 over 30 plus 1 over 30, which is 3 over 30, or 1 over 10. And since 1 over R equivalent is 1 over 10, I'll get R of BCD when all those 3 things are combined as 10 ohms. So let me rewrite here for clarity. Here it was, this R equivalent is simply BCD. We're just calling it by a different name to clarify what we combined that went into that. 1 over R BCD was equal to 1 over 10, which makes R BCD equal to 10 ohms. So I'm going to redraw that over here. So I've got the same battery, same resistor A, but now B and C and D have all been combined into a single resistance, which we call BCD, and we have determined that that was just 10 ohms. So this is still A, and the battery is still 15 volts. And let me just write this value over here as well, 5.0 ohms. So now this has become a simple circuit, and even though I have this bend over here, we can see that A and BCD are simply in series. The same current that goes through A has no choice but to go through BCD as well. So as a last step, I can combine those two, and let me do that in red. So I've got R equivalent for A, B, C, D, all 4 things combined, would be RA plus RBCD, which will give me 5 plus 10 equals 15 ohms. So as my final step of the simplest circuit, we have reduced this to a very simple circuit of just 1 resistance and 1 battery. So I've got a 15 volt battery, and the numbers worked out to be that this was A, B, C, D, and it was simply 15 ohms. So I've got current going from positive to negative, so in the clockwise manner, and the potential difference across this one bulb is exactly the same as the potential difference across the battery. These are ideal wires, so the potential at this point at the negative end of the battery is the same as at this end of the bulb. The potential difference at the positive end of the battery is the same at the other end of the bulb. So this difference being 15 volt and this difference being 15 volt, they are both the same. So then I can use my Ohm's law and figure out the current in this circuit. So the current in this circuit would simply be delta V over R. Delta V across the bulb is 15 volts, same as the battery CMF. The resistance is 15 ohms. So this gives me a current of 1 amp. So now our objective was not to solve this very simple circuit, although we have got an important piece of information that the current supplied by the battery is going to be 1 amp. But our question was to figure out the current, the potential difference, and the power of each resistance in the original circuit. So in order to do that, now that we've gotten all the way down to the simplest circuit, we got to go backwards 1 step at a time to figure all that out. So when we go back to this previous step, the current out of this battery is also going to be 1 amp. So if I have I over here, it's also the same as 1 amp. So I've got that current of 1 amp going through resistor A, and then it's going through resistor BCD. So we already answered one minor part of this question. We know the current through 1 resistance so far. And if we know the current through bulb A is 1 amp, we can immediately figure out the potential difference across it, because according to Ohm's law, we have delta V equals minus I times R. For a resistor, we know the current is 1 amp. We know the resistance is 5 ohms. So the potential drop across this bulb is going to be 5.0 volts. The negative sign simply says that it's decreasing in the direction of current. And if we know that, we can just say that delta VA is 5.0 volts. So as we go along, I'm going to collect my final answers over here. We got the current through A already as 1 amp. We got the potential difference across bulb A as minus 5.0 volts, where the minus simply stands for the fact that it dropped in the direction of current. And the power was I times V, which also we can write as minus 5.0 watts, simply to indicate that this power is consumed or dissipated by the bulb as opposed to being produced by it. Okay, now that we have done this fourth circuit and the third circuit, now we got to go back to the second version over here. So we still have the current out of the battery as 1.0 amp. That hasn't changed, and all of that goes through bulb A, but then it splits here at this junction, and it splits based on the resistance in each part of that junction. We also know that the potential drop across A was 5 volts, and the EMF of the battery was 15 volts. So let me write some of that over here. And so if I assume that the potential at this negative end of the battery is 0 volts, it's the same 0 volts over here and the same 0 volts over here, which means one end of bulb B and bulb CD is at 0 volts. The other end, I gain 15 volts by going through the battery, but then I drop 5 volts by going across bulb A, so I'm only left with 10 volts. So let me just write those numbers down over here for convenience. If I have 0, 0, 0, 0, 0, all these places, it's 15 volts over here. It's 15 volts just before I get into bulb A. By the time I come out of it, it has dropped by 5 volts, so it's now 10 volts. So in this part of bulb B, it's going to be 10 volts, and bulb CD, same thing, 10 volts. Now let's look at bulb B. I know the potential difference across it, it's 10 volts. I know its resistance, it was 15 ohms, so I can figure out the current through it. Let me do that over here. IB is simply going to be delta VB divided by RB, and delta VB is 10 volts. The resistance was 15 ohms, so this gives me a current of 0.67 amps. And I can do the same calculation for this combined resistance CD. So let me go ahead and do that. I see the current in this second arm of this parallel circuit is going to be delta it's ICD, delta VCD divided by RCD. I know that the delta VCD is 10 volts. The RCD is 30 ohms. So this gives me 0.33 amps. And when you add these two, you get 0.67 plus 0.33 gives you exactly 1.0 amps, which makes sense because there is a junction over here into which the current coming in was 1 amp from the battery. 0.33 went over here, 0.67 went down, and the total amount of current coming into the junction equals the total current going out of the junction. So we have verified Kirchhoff's junction law. And it's useful whenever you get a chance to verify these simple laws to make sure that there is no math mistake you made in doing these calculations. So let's see what all we have gained to fill into our final answer bucket over here. So for the resistance B, we know the current through it is 0.67 amps. We know the potential drop across it in the direction of flow of current is 10 volts, so just write it as minus 10 volts to follow our convention. And the power is simply the current times the potential difference. So let me write that over here. P is IV, which equals I squared R, which equals V squared divided by R. Any of those forms you use, you will get the power simply as minus 6.7 watts for bulb B. I still don't have the answers for C and D because they are combined in this circuit. So as a last step, I go back to this circuit over here in purple, and I can work out those details. So I know that the current going through this arm in the previous circuit was 0.33 amps, and that's not changed, so that's still going to be the same. And that same current goes through C as well as D. So I already have the answers to the current for C and D which would simply be 0.33 amps and 0.33 amps, same current because they're in series. The potential difference is now easy to calculate. Delta V across a resistor is minus I times R. So I've got minus 0.33 times, for C it is 10 ohms, so that will be minus 3.3 volts. And for D, it will be minus ID times RD. This was IC and RC. Minus 0.33 times 20, which would be minus 6.7 volts. You'll get 6.6, but if you used another decimal, it'll be 6.66, which will translate to 6.7 volts. So I've got the potential difference across C as minus 3.3 volts, the potential difference across D as minus 6.7 volts, and then the power is simply the multiplication of these two, which will give you minus 1.1 watts and minus 2.2 watts. So I've got all the answers I was after, but let's just quickly pause and verify a couple more things to make sure we haven't made any mistakes. So we already verified the junction law over here. Now let's see if we can quickly verify the loop law. I'm going to use two loops. I'm going to use this loop over here and see if the potential difference across that entire loop is 0. So I start from the negative end of the battery at 0, gain 15, drop 5, I'm down to 10, and then going through B, I drop another 10, I come back to 0, so that's verified. I can do the same by going through this outer loop. I gain 15, drop 5. By the time I go through C, I drop 3.3. I'm left at 6.7. By the time I go to D, I drop 6.7. I'm back to 0, so that works out. All right, let's call that a victory and be done with this problem here. So in this slice of physics, we learned how to analyze a more complex circuit. We did that by making the circuit simpler sequentially, one step at a time, by combining two resistances each step. And then we used Ohm's law and Kirchhoff's laws, the junction law as well as loop law, as required to determine the unknowns or to verify that we were doing our calculations correctly. Thanks for watching. I'll see you soon.